So I think we're live now. Yep. So we are live. So folks, what I was saying before I forgot to start recording. We have a variety of students in our classes, and there's math majors, there's chemistry, biology majors, there's physics majors, there's computer science majors, and so on. So this is not a specialized calculus section like maybe if you were at a bigger university, maybe you would get some specialized calculus for maybe for physicists or calculus for I don't know, for engineers or something like that. So it's like everything for everybody here. That's why this particular section would be useful, for instance, for somebody who is not necessarily a math major, but someone like a physics or a chemistry major, because some of these problems have so more or less a more practical flavor. So as a math major, you're probably never gonna see, unless you yourself become an applied mathematician, you're probably never gonna see problems like this one that we'll do here with, fencing yards and maximizing the cost and things like that. So those are good problems, but they're applied problems for somebody, say, with a degree, with an interest in economics, somebody with some interest in physics or in chemistry or some other things, some other areas. But the mathematical content is nothing new there. So there's nothing new that we learn in this lesson. So that's what I'm trying to say here, that if you're a math major, the benefits coming out of this type of lesson are minimal. So benefits are mostly for folks who aren't necessarily math majors. That being said, it's a good idea too for math majors to understand, how to apply this in practice, because maybe one day, unless you become a very specialized in very much abstract math like algebra or geometry or something like that, some of these problems, if you become an applied mathematician or you go out in industry and you apply these notions, some of these problems may resemble those that you see in the real world. However, I would say that these are halfway there. These are artificial. Some of them are artificial examples, not necessarily like those that you see in the real world. So again, we're kind of going halfway between math and the real world, so to say, here with these problems. And I'm going to do example one from the book. So today we're starting 3.7. Okay. All right. So lesson 3.7. And the title of this lesson is, okay, optimization problems. One second, let me move these out here. So optimization. So there are applied areas of math that where you would find this kind of thing very useful, but generally, I would say that this has a focus on more or less, if you want, some type of practical problems, more like in the sense of mathematical modeling of some real life situations. Um, and I'll give you some examples. But before I do that, let me just, so you notice that we were at lesson 3.5, the one with the graphing. And we shot straight to 3.7. So you might wonder, where is 3.6? 3.6 is gone. And I'll explain you why that is gone. It has to do with the fact that the title, so you can see from the title of 3.6, it's called Graphing with Calculus and Calculators. Now here's the deal. This book was written, more than 30 years ago. So at the time, the calculating with calculators, then graphing things was a very tricky thing because the technology was not developed. Nowadays, this is a waste of time, essentially, talking about graphing with calculators. Desmos can do anything and everything you can think of in terms of graphing. So 3.6, we skip. If you want, do Desmos. So all the graphs that you ever need in calculus can be easily done with Desmos. Just typeset the formula there, and then that's gonna spit out the correct graph. So this is gone. So we essentially, if you want, you can say it's too much of an outdated lesson to even worry about discussing anything there. So Desmos takes care of the issues there. All right. So we are going to again start with some optimization problems. Now let me just wipe this out here to give myself a little more room. So okay, I'm gonna wipe that out. There we go. So folks, the first problem that we'll do here is example 1 from the book. This is a very good problem in the sense that it really captures, in a nutshell, it captures what we're talking about here in terms of what kind of real life situation do we model. Well, here's the real life situation that we model. It says here that a farmer has 2,400 feet of fencing and wants to fence off a rectangular field. So this is my farmer. It's got a rectangular field, but over here at the bottom of a field, somewhere on the south side of a field, so let's say this is north and this is south here. On the south side of a field, this person has a river. So this is a river over here, which may be thought of being essentially a straight line or something. So, the bank of a river could be anything, but in this case, so we think about it as more or less a straight line or a little curvy like this. So this farmer, again, has 2,400 feet of fencing. So with 2,400 feet of fencing, this person wants to enclose a rectangular field like that. And the question is, what should the dimensions of this field be, again, rectangular field, so that the area is maximum? So we want the area of this field to be maximum. So this is something that we would like to address here. And here's how we go about doing these kind of problems. Now, all of the problems that we're going to do here, or the ones that are in this section, follow some type of pattern. So that's why I'm saying that they're not necessarily the most realistic questions, because there's a pattern to them. So if there's anything in practice that you will find in practice as an applied mathematician, is that there is no pattern really. So you yourself will have to sort of design the model, and hopefully you arrive at one of them that looks like this. So the pattern of this problem, there is a geometric shape that's given. In my case, a rectangle. And this geometric shape, I want to find the maximum area. So there's a question about the area or the length, the perimeter or length or whatever. So some sort of measurement associated with that geometric shape. And we would want to describe it as precisely as possible. How do we do that? Well, to do that, we are going to choose over here, because it's a rectangle, so we are going to display the elements of a rectangle. A rectangle has a length, which is this side here, and a width, which is this side, these two sides over here. And we could call length, you know, the size, the side across along the bank of a river. So we could call that L as well. The problem is that the farmer doesn't need to put a fence but on the side of the river. He only needs to fence, you know, these sides that are off the river, so the width, the length, and another width again. So that would be his fencing. So I can express the fencing that's given here in the problem, this one, 2,400 feet. I can express that as 2,400 equals length, right? Because we use one length to cover, and two widths, this one here and this one here. So that will be the type of fencing that we use here. All right, and that gives us, folks, so all these problems will have a situation like that when you will be given either the area of something or the perimeter or something like that, and that will give you a constraint. So this is a constraint between the length and the width. So the length and the width couldn't just be anything, you know, you couldn't have a length of 100 and a width of 100 because that will be a total amount of fencing of you know, 100 plus another two is 300, right? So but we need 2,400 fencing, feet of fencing, right? So that's giving us the constraint. And the question now can be formulated, and this is again something that most likely people do in practice. They formulate the question mathematically. This is an important part of the process. So in practice, that's not given. You are so again, you yourself have to figure these things out on your own, and formulate the question correctly and then solve the problem. So in practice, folks, before you solve a problem, so let's say one of you will go and work in industry and will design you know fences like that. So your manager will say, "Here, Johnny, you have 2,400 feet of fencing. Please find me the maximum area." Where would this be useful? Well, that is useful, folks, for people who work in the construction industry, the building houses. So when you build a house, you know, you more or less know your amount of wall that you know you could afford based on the cost, and you would want to maximize the area, the square footage of the house, right? Because, well, if I have, I don't know, 2,400 feet of fencing, not for a house, not a fencing, of wall, right? So measured linearly around the house, what's the point of making a small area house when I can make a bigger area house and I can sell it more expensive, right? So that's the type of question that you need to deal with, and that's what engineers who build houses solve. They solve these kind of problems. And when you're an engineer, this is what you do. You try to figure out your given things and you try to maximize or minimize, depending on the situation, the quantities involved there. But before you do that, again, you have to formulate your question mathematically in a clear way. And the question here is area, area, I want that to be maximum. Let's see what area is. Area is L times W, because this is a rectangle, folks. But this is not a good formula for me because, well, I don't know how to find the maximum of a function of two variables. Both L and W are variable. You will be able to solve this problem with Lagrange multipliers in calculus 3. But until you get there, you have to figure out another way of solving this problem. And the way to solve this problem is to write this area as a function of one of the two variables, either L or W. How do you do that? Well, there's an easy way to solve for L from this formula, from the formula above, the formula giving the fencing. So you can solve for L there, and you can see that L is 2400 minus 2W. And then you take that and you put in this formula. So this is going to be L, but L we just said was 2400 minus 2W times, and then it's going to be times W, L times W. So this is going to be the result of the area. And that is now a nice function, because we can write the product d times negative 2W is negative 2W squared, and then plus v, I'm sorry, v, I'm saying W, folks, times 2400 is plus 2400 W. So this guy here is the function that I want to maximize. And I can employ the methods of calculus. So I can actually graph this particular function, this one here. And unfortunately, I'm working with large numbers, so 2400 is a large number. But I can graph it, I can zoom out a lot in Desmos, and I can pull Desmos. I'm going to pull Desmos right now. I'm going to graph that function, and we'll figure out easily where the maximum is in a second. So let's do Desmos here. Come on, Desmos. All right, so Desmos is taking a little bit to, not sure why it doesn't download. Uh-oh.